Hello everyone, here's the answer key video to the practice test 1, page 1. I've kind of recreated some of the worksheet here because I don't have a printer at home, so I'm working off of the PDF and then just working on paper like some of you guys have been doing. So we have these two situations, situation A and B, where both of them, like we demonstrated in class, are spinning a mass around. I forgot to draw the mass. Spinning around in a circle, and both of them, everything about the situation is the same except for the mass. This one's 1 kilogram and this one's 2 kilograms. So number 1 asks, how does the speed of A compare to the speed of B? So just to kind of show a little bit of work for number 1, we know we have this equation d equals vt. Distance is speed times time. And so that means that if we kind of rearrange this, divide both sides by t, we get velocity or speed is equal to distance divided by time. So the speed that an object takes depends on the distance and the time. And so in this case, the distance that it's traveling is this circle, which is this the distance around a circle is the circumference, which is just 2 pi r. So 2 pi times this radius, and then in this situation, it's also the circumference, which is 2 pi times the radius. And since they both have the same radius, the distance for both of them is the same, right? This is the same circle as this circle. If one of them was traveling a bigger distance, then we'd have a bigger radius, and they don't. And then the other question is, or the other thing that you need to know for speed is the time that it takes to travel that distance. So the time in this one is 1 second, and then the time in this one is 1 second. So that's also the same. So since they're both traveling the same distance and they're both doing it in the same amount of time, that means that their speeds are the same, which is C. A equals B, so they have the same speed. Number 2 asks, what is the force in each case? So looking at the top of the page over here, we see that our net force is the centripetal force. So central net force is equal to mv squared over r. So kind of the same thing we did here. We're just basically looking at how do each of the variables compare. So to know the force, we need to know the mass, the speed, and the radius. So our radius, we can see in both of them, again, it's the same. And then the speeds we just said are the same. So this is same, and this is same in both cases. But the masses are not the same, right? In this case, our mass is 2 kilograms, and in this one, our mass is 1 kilogram. So these are not same. And in fact, B is bigger. So because these things are the same, they kind of don't matter because they're the same in both problems. But this one has double the mass of this one, which means that B has double the mass of this one, which means B will have double the force of A. So A is less than B is what that's saying. So that means we need to, the answer for 2 is B. And if this is not convincing to you, you can always just make up a random speed and make up a random radius. So you could just say, I don't know, let's say they're both going 5 meters per second is their speed, and their radius you could say is half a meter. Honestly, I made these up. You can put anything that you want, and then you just plug in 2 for the mass in this case and 1 in the mass for this case, and then actually evaluate it, and you'll see that the B's force is bigger because the mass is bigger. Number 3. So I'm not going to redraw the diagram because you have it here, but we're doing sort of the same situation. How does the speed of A compare to the speed of B? So, same situation, that both the radii are the same, but in this case, the masses are the same, but the time is different. So the first question, number 3, is asking about the speed. So sort of going through the same thing above, I'm going to look at that equation, V equals D over T. And, so how do these things compare? So the distance, again, since they both have the same radius, they both are, the distances that they travel are going to be the same. but the times in this case are not the same. So in part B, it takes longer. It takes 1 second. So B is 1 and A is 0.7. So we take the same number and divide it by either 1 or by 0.7, and then we find the velocity. So the sort of, if you don't want to look at the numbers, you can just basically think about the fact that they're both traveling the same distance, but one is doing it in less time. So if two people race and they both are on the same distance, but one person makes it that distance in less time, that means they must have been going faster. So the one that did it in less time is going faster, which is A. So A is greater than B is the one we want. So that's letter A. So A is faster than B. And again, if that like sort of conceptual argument isn't convincing, you can just make up numbers for this and find out. So you do like for A, you would do velocity is distance, and you just make up a distance. Let's say it's 5, doesn't matter, divided by 0.7. And for B, you would say V equals 5 divided by 1, and you'll see that this number is bigger than this number. 4 asks about force. So let's do some math for the force. We can kind of look at like, so for A, what's going on? So our force, I'm using this equation again, our central net force is equal to mv squared over r, and then B also mv squared over r. So how do their forces compare? Well, how are the masses compared? They're both 1, so they're both the same. So like same. How does the r compare? Also same. So those are so far going to make the equations the same because there's no difference between the two m's and the two r's. But how do the velocities compare? Well, from number 3, we just said that v is the bigger one, and this one, v, is the smaller one. So we take the same mass, we divide it by the same radius. So like this part of the equations are the same. So then when we multiply them together by a bigger v, we're going to get a bigger force, and this smaller v is going to get us a smaller force. Again, if that's kind of unconvincing, just sort of do the same thing we did up here. Just make up numbers, plug them in. And then if this v is bigger, then we'll get a bigger force. And if this v is smaller, we'll get a smaller force. If you plug in numbers, you'll find that that's the same thing. So we know that, how does the FC, so A is bigger than B. Conceptually too, we're spinning like the same mass faster in one case and slower in the other one. You're gonna have to like kind of whip the thing around faster, or harder to make it go faster. 5, which of the following is true for an object traveling in a circular path at a constant speed? So if we're spinning the thing around at the same speed the whole time, it's not speeding up or slowing down, which of those is true? So I guess I'll just kind of go through them one at a time. Which of these is true? Its speed is constant, so its acceleration is 0 because the net force is 0. So that one is not true, because even though the speed is constant, we just said that the net force is not 0. There is going to be a central net force. So the force is not 0, so that can't be right. I'm going to look at C now. Both its speed and velocity are constant because, I think we're missing a cos in that, because the direction is constant. That's not true. The direction is not constant. The direction is constantly changing. Like when you're here, the thing is spinning, pointing that way, and when it's here, it's like going in that direction, and when it's here, it's going in this direction. So the direction that it's facing is constantly changing, so that's false. And for D, both its velocity and acceleration are constant because the direction is constant. Again, false, the direction is not constant. So then we're looking at B, its speed is constant, that is true, but its velocity is changing because the direction is changing. That is true, so that's the one we want. I've mentioned this before, but the way I like to think about it is like, we're going, when the thing is here, it's going in that direction, and then as it goes this way, it slows down in that direction, but speeds up in this direction. So you can think of like horizontal and vertical are treated differently. You're speeding up in one direction and slowing down in the other. Last one, 6. Astronauts quote unquote float. Oops, my computer's going to sleep. Wake up. Float in space in the space shuttle because A, they are weightless since the gravitational force on the astronauts is 0. So that's just not true. We know that if an astronaut is orbiting, it still is, he or she is still experiencing gravity because they're not far enough away. B, there is no air in space to hold them down. The first half of that sentence is true. There is no air in space, but air does not hold you down. Gravity holds you down. So that's like, that just means there's no air resistance to slow them down, but it doesn't have anything to do with, keeping them from going to Earth. And D is obviously false now because all of the above is not true. So C, the astronauts in shuttle are all falling around the Earth together, so the astronauts are not pushed outward by the shuttle. So that's the case that is true. So the astronauts are being pulled down, but not, they're going so fast that the gravity doesn't actually pull them down. It just sort of changes their direction.